Last section here has two somewhat unrelated concepts. Where we start is with a definite integral. So this is just using the same general idea of e to the u, except instead of getting the plus c's, we're going to end up plugging in the 0 and the 1. So where we begin is identifying what the exponent is on the exponential. In this case, it's negative 5x squared. We're going to use that as our u. Once we've identified our u, we need to take the derivative of both sides. So the derivative of the left side is just du. The derivative of the right side, the 2 comes down, and it becomes negative 10x dx. When I look at my original equation, I don't have this negative 10 in with the x dx. So I need to introduce it. The way that I do that is I keep the 0 to 1, I keep the e to the negative 5x squared, and then when I put in negative 10 here, I need to undo it with a negative 1/10 out front. That way, if I multiplied this negative 1/10 by this negative 10, I'd get back to a positive 1, or in other words, I haven't changed the problem mathematically. I still have this x and this dx here, which means that when I go to integrate, negative 1/10, the integral from 0 to 1, I really have e to the u du. Now notice that once I've gone to the world of u's, this 0 and 1 are technically incorrect. I could plug them in here to figure out what they would be as new limits of integration in terms of u, but the way that I've shown it last lesson and want to continue to show it is that I'm just going to put x back in the end and use these as the limits with respect to x. So when I integrate e to the u du, I get negative 1/10 e to the u, which is going to be evaluated from 0 to 1 once I put the x back in. So putting the x back in, I get negative 1/10 e to the negative 5x squared being evaluated from 0 to 1. I start by putting in the 1. When I put in the 1, I get negative 1/10 e to the negative 1 squared is 1 times 5 is 5. I'm going to subtract from that when I put in 0, which gives me negative 1/10 e to the, when I put in a 0, 0 squared is 0 times negative 5 is also 0. This e to the negative 5th goes to the bottom as a positive 5th, so I get negative 1 over 10 e to the 5th. This negative and this negative make a positive, so plus, and e to the 0 is 1, so it's just 1/10. This would be a perfectly fine final answer if I was given to you on a paper test. In Cengage, they probably ask you to go to a certain number of decimal places. So I'd want to put into my calculator negative 1 divided by parentheses 10 second the ln button, which is on the left side, to get to e to the x, e to the power of 5, and parentheses plus 1 divided by 10. When I put all that in, my calculator tells me an answer of 0.0993. The second problem here is really just learning how to use inverse functions, e to the x and ln of x. So basically, when I have e to the ln, the e and ln go away, and I'm just left with x. The same way, if I had ln of e to the x, the ln and e would go away, and I'd just be left with x. The reason this happens is because they're inverse functions. The same way, if I take the root of x squared, I get back to x, because square rooting and taking something to the second power are inverse functions. Or if I do x plus 1 minus 1, I get back to x, because adding 1 and subtracting 1 are inverse functions. So if I start there, I can just rearrange this problem, y equals the ln of e to the 5x squared, and say, well, I'll get rid of the ln and e, and just turn this into 5x to the 6th. I've now made the problem easier to do, but I haven't done what's been asked yet. What it asked me to do was find a derivative. So really what I need to do is take a derivative of this 5x to the 6th. To do that, I just use the power rule. 6 comes down, 6 times 5 gives me 30. X, subtract 1 from the exponent to the 5th. So the real key here was understanding that the ln and e were inverse operations, and I could just look at the exponent and find the derivative of the exponent to complete the problem.